Hello, students. So today we are going to begin with the next part, the second part of linear algebra, and that is introduction to eigenvalue problem. So the word eigenvalue is known as means it is a proper value, and why does it why is it very important to know about the eigen things or the eigenvalues? Eigenvalues, then eigenvectors. So eigenvectors are related to eigenvalues. You must have heard about it. And before we proceed with this, we need to know that you are familiar with matrix algebra, determinants, and vectors. Okay, so matrices are rows and columns in a different or definite order. Determinants is a numerical value, and vectors is, say, if A is equal to, say you have this in this format, say 2 3, then you could say there is a single vector. So they are basically, or if you have a vector matrix like this, then this, and this. So you could say that there are two vectors in A, say x1 equal to 3, 1, and x2 equal to 1, 3. Okay, so here it is. So now, so if let A is a matrix, so you have and x is a vector. So this means basically multiply matrix A with the vector x. Since you know that this multiplication can be only done if there are certain, so if A is a m by n and x is a n by say p, then we will get a vector whose length will be m by p. So these are the basics of matrix multiplication. So we say then it is confirmed. So here, so what happens? So let us take an example of matrix multiplication. Say I have a vector matrix A, and that is 1, 2, 2, 1, and a vector x equal to 1, 0. Okay, so we have this, and I would like to also here show you that this is this, and if you have a axis system, so your vector, the vector which we are looking at is here, it is this vector, this is the vector. Okay, so this one is your vector, and yeah, put it here 1 0. So here is a vector, and this vector is, we can write it as 1 and 0. Okay, and this is the x-axis and this is the y-axis. Fine. So now that we know that we can multiply, we will check the dimensions here. It is multiplicable. So we will use our knowledge of ax is equal to 1 to 1. And this is a very simple multiplication because we know that these are called the standard elements vector forms. So we have 1, comma 1, 2. So we write it as this. So here, what happens? This, if you look at the visualization here, so here this vector I would like to take it in this way from here to, sorry, not like this, just a minute. Yeah, so this vector would be drawn like, let us do it this way. It would be like this. Okay, so what do you see? This is the vector which I've got now, and this vector is denoted written as 1, 2. Okay, so there are some observations here which we will write down. So what observation? X, the vector x, first observation. So the vector x equal to 1, 0 makes an angle 0 with x-axis. Okay. And it has a magnitude is equal to 1. Okay. Second point, we see that the vector ax, so let us call the vector which we multiply ax is equal to, say, some vector b. Okay. So the vector b, which is equal to 1, 2, makes an angle, say, let us call it theta, and here I mark it as theta. Okay, theta, and with positive x-axis. Positive x-axis. And if this is b, then what is the length of b? The length of b is equal to square root of 5. Okay. So as we have multiplied the initial vector x with a matrix A, we get a vector, okay, and this vector is not same as the initial vector x or the original vector x. Okay. So what has happened? The vector b was stretched. So what are the 2 points? You can say that here in this case, so from here we can write that. So let us note down what are the important parts we have found out here. That is, let us note it down. So first point is our main this one. The first this one is that the vector x equal to this on being multiplied by the matrix A equal to 1, 2, 2, 1, rotated by an angle theta and was stretched by root 5 times of this vector. So this is what is happening. So this is the general picture, or you can say that A has acted on X. That means it has transformed. A has transformed. So you can say like what is you're taking from this particular this one, you put right here that the matrix A, we could write here, sorry, we can write here the matrix A, acts on the vector x, acts on the vector x, changing the direction as well as the magnitude of x. So this is what you see. So now this comes from simple multiplication of a matrix with a vector. So now let us go on to the next part, that is about what happens. So what is the first some questions, okay? So first question is, are there any vector, okay, that can be associated with a matrix A, okay, such that, where are there any vectors, say x, okay, such that when A is multiplied to x, it here we can write, instead of writing it, we could write here the matrix, the vector Ax does not undergo any rotation. Okay. So this is the first question. Next, if it is possible to find such a vector, X, satisfying the above property, then how do we find that? Okay. So what I'm asking is, that means if you look at this, I'm saying answer is for this is yes. If yes, okay. So if answer for one is yes, if yes, then Ax will be equal to some lambda times of x. How do you? That means what? When the matrix A is multiplied to a vector, then it is becoming some multiple times of this vector x, same vector x. That means what happens here is, what should happen is, so we have this is, okay, say this is the initial vector. Let's take one vector here. So this is the initial vector. Let us use a different color here. So this is the initial vector. Now we'll call it x. Okay. Yeah. So I take a green color. So this is the initial vector. So it has some. Okay. So this is the vector x, and you have now multiply this vector with a certain multiple of this. So what happens? You get a vector which is slightly maybe longer than this, but as you can see, it is superimposed on the original vector. So this is what is representation of. So this is your x, this is your y, this is the original x, and this is ax. So there is no change in the theta value, or there is no rotation. So lambda could be, lambda is a scalar. So this is what. So how to find this? So if we have this, so the first is we need to find a vector. We need to find, so what is this vector? If you have, suppose this vector is not undergoing any rotation, it has only become stretch, such a vector x satisfying the vector x satisfying the equation is called an eigenvector. Eigen, which means, eigen means, yeah, it's a characteristic or a proper value of a vector. So eigen here implies, it means proper value. And the corresponding scalar lambda, again satisfying the equation, satisfying ax equal to lambda x, is called an eigenvalue. So far we have seen that this is from where the eigenvalue problem comes. The eigenvalue is a particular scalar value which is associated with an equation of this kind, and this equation which we have written here, ax equal to lambda x, is known as the eigenvalue problem. Eigenvalue problem. Now, this has many various applications in different fields, in machine learning, in physics, in other fields where you want to go for image compression. So let us now see how to find a eigen. So the problem is to find, so now we are zeroing into to find the eigenvalue and eigenvector, okay, of a matrix E. Okay, beginning with a matrix A. So let us take an example. So the matrix for our discussion today is given as A is equal to 8, 3, 2, 7. Okay. So we need to find a vector x, eigenvector, and eigenvalue lambda. So now if I write the, so we are given this, you are given this. It's the first step. So we set up an equation, we set up an eigenvalue problem. eigenvalue problem. Okay, so how do we do this? We write here, setting up, we write A, okay, is equal to yeah, we have A equal to, we'll use some color here, black, x, yeah, it's x. So we write here A, and then we use different color here, x, lambda, x. So this is the problem. Okay, so A is a matrix, lambda is a scalar, x is a vector, here x is the same vector. So to solve this, what we do, we can equivalently write it as A x minus lambda x equal to 0. Now, we do not, this is not a correct thing. We should write it as ax minus lambda times of ix equal to 0. Because lambda is a scalar and this is a matrix, so we have to write. So if now you have a correct form of the equation, that is ax, or we could write a minus lambda I times of x equal to 0, where x is not equal to 0. We want to find this. So what we take? We take the determinant a minus lambda I is equal to 0. So this is a value which. So let us take it. So here in this case, what will be a minus lambda I for this particular problem? So here you see 8 is given 3 and it is a 2 by 2. So we will take minus lambda times. We'll take a 2 by 2. I is an identity matrix 1, 0, 0, 1. And this becomes, after solving and matrix operations, lambda 3, 2, 7 minus lambda. So now we need to find the next step to find the what is the next step? Find determinant. So how to find the determinant? So we take 8 minus lambda, 3, 2, 7 minus lambda, and equate it to 0. So find determinant and equate it to and solve a minus lambda I equal to 0. Now, when I solve this, what do we get? 8 minus lambda, 7 minus lambda, minus 6 equal to 0. And further solving it gives me 56 minus plus lambda square minus 15 lambda minus 6 equal to 0. And this gives me an equation which is called a quadratic equation in lambda. Now we call this a characteristic equation. So this kind of equation which we get here is known as a characteristic equation. Characteristic equation. Okay. Solving this by algebraic method, we get lambda is equal to two values, we get 10 and 5. Okay. So now my claim is lambda 1, we'll take always a larger value first, and lambda 2 equal to 5. These are the two eigenvalues associated with A equal to 8, 3, 2, 7. Okay. So we have now two problems. So what our problem is, the eigenvalue problem is A x1 equal to lambda 1 x1, and another is a x2 equal to lambda 2 x2. So if I plug in the values, I get ax1 equal to 10x1, and here I get ax2 equal to lambda 2 x2. So we write the this here 8, and we have 3, 2, 7, and we know that according to the multiplication rule, we have to select some vector which is two-dimensional vector. That means it has x11, x12, and this one 10 times of x11, x, where you can say x1 is equal to x11 and x12. So solving this, we get 8 minus 10 and 3, 2, 7 minus 10, we get x1, 1, x1, 2 equal to, when you put it on the side, you could also write it like this to make it more sense for you, 10x1, 2. So this will become 0, 0. It is a vector. So further solving it, we get minus 2, 3, and here 2 minus 3, 2 minus 3, and we get a x11, x12 equal to 0, 0. So we get, if you multiply this, if you could multiply this or this, it always results into the same equation. So we are not writing it twice, we are writing it once. And solving it, as you know, we have to take it on this side. So we get 3 by 2 x12. If we have x12 as a multiple of 2, that is 2, the first multiple I'm taking, next one becomes 3. So what do we get? We have x1 equal to x11, x12, and that is going to be 3, 2. So this is the eigenvector. So now I'll rewrite this equation. How will I write? That A, okay, 3, 2 is equal to 10 times of 3, 2. That means, it means here, when A is multiplied to the vector 3, 2, the eigenvalue, the eigenvector 3, 2, the eigenvector is stretched 10 times. So we write when A is multiplied with the vector, which vector? The eigenvector 3, 2, it is stretched 10 times. Okay, fine. So if that is so, let us look at the visual here, the visual representation. So we get this is it. So we have a set, this one, and we have axis here. I have put this axis here. The reason is that, yeah. So this is the axis, okay, and the vector is your okay. So we are taking a vector. Vector is 3, 2, and if 3, 2 vector was this, let us take a different color and show 3, 2 first. So 3, 2, say from here was this much, 3 and 2, so it was bit like this. Now after the multiplication, what has happened is it has stretched, okay, this yellow vector, it has stretched, simply say it here, okay. So now we have these two things here, okay, so let me write it here. So what is the picture here? So this is your x-axis, this is your y-axis, and initially we have this eigenvector 3, 2, and the eigenvalue is, this becomes 30 and 20, which is the result of multiplication of a on x. So there is no rotation, only there is a stretch. Similarly, working on the same lines, if we work on the same lines and solve this, we get uh, 8, okay, 3, 2, 7, and this time I'll put x2 equal to x21 and x22 for clarity. And we can say here, okay, we'll write here x21 and x22 equal to 5 times. So here we will take 5 times and we'll write here, because lambda 2 is equal to 5, okay. So we have x21 and x22, and we could write here 8 minus 5, 3, 2, 7 minus 5, x21, x22, and this becomes 0, 0. Solving it, we get two equation, 2x1, 2x21 plus 3x22 equal to 0. Further solving it, we get, excuse me, this should be 3 and 3. So this is 3 and 3. Yeah. So here we have 3 3x121 plus 3x22 equal to 0. So x21 equal to minus x22. So if you put x22 equal to 1, then x21 equal to minus 1. So what is the x2 vector? Which is 1 minus 1. And what is the lambda 2 equal to 5. Now again here we have a, so what is this equation now? What is the equation? So the equation for this part is a times of 1 minus 1 is 5 times of 1 minus 1. Okay. So what would happen here? Again, there will be a stretch, and we'll see here what happens here. So we could see here that, go to the next thing. So we have two things. One is a x1, which is 3, 2 equal to 10 times of 3, 2. And the next one is a, it was minus 1. Yeah, 1 minus 1. 1, yeah, it is 1 minus 1 equal to 5 times of 1 minus 1. So we have solved a eigenvalue problem, and let us now look at comprehensively what it means. So it is actually, if you look at this one, you'll see here. So this is our axis system, okay, and here for this one, again an axis system. So what you could do is, okay, we could do it in the same one, or we can do it in separate. So if you look at this one, so we have first 3, 2, 3 is bit like this, 3, 2, 3, 2, and it has gone up to say what has happened? The change is about. So I'm going to use a lighter color to show that it has gone till here. Okay. And what about this here? So what happens here? If we have this 1 minus 1, 1 minus 1 is somewhere here, 1 minus 1 is this way. And if you want to use a color here, a different color, so you see here it goes how many times? 5 times in this direction. So this is the direction. So here you see, if you look at this, you'll see here that this is first one 3 2. Yes, this is 3 2, and this is 30 20. Here similarly this is 5 minus 5, and this is 1 minus 1. So this shows that this is the eigenvalue problem, and here in this eigenvalue problem, the vector which is 3 2 here, the first eigenvector 3 2 lambda 1 gives us the first eigenvalue, and the corresponding vector is 3 2 and lambda 2 equal to 5 and x2 equal to 1 minus 1. So this is it. So we solved the eigenvalue problem, and we have seen here that when we multiply A with this, we are noting that there is no rotation except that it is stretched. Here it is stretched 5 times, and here, so you could very well write here that it is A times of 3 2, and here you could write that this is A times of 1 minus 1. So this is what it does. So eigenvalue problem, eigenvalue can be found out, and it does what? It does not rotate the vector, but it gives a same direction. So here you can see this is one axis system, x and y, and the second axis system is given by x1 and x2. This is x1 and x2, and this is given as 5 times of x2, and this is given as 10 times of x2. Here they are mutually 90 degree x and y, but the angle between x1 and x2 is not 90 degree, it is some angle alpha. Okay, so there are various applications. The main applications you could look up is in the following. One is principal component analysis. Principal component analysis, which we will take up in the applications of this. Second, in physics, we have stability analysis. Stability analysis. Then more, so you can look up page ranking, page rank. Okay, so these are the many different ways in this the concept of eigenvalue has been used. Thank you for your